Okay, I would like to start by thanking the organizers for the invitation to speak at this conference. It's a great pleasure and a great honor. So before mathematics, I wrote something to Michelle. Let me just write it. So during my PhD thesis, my advisor, which was Bernard Keller, always said to me that Michelle was special. So at the time, I was very innocent and did not fully understood Keller's words. But when I finally met Michelle, this was 10 years ago at NSRI in Berkeley, I immediately understood what Keller was saying. So Michelle was this outstanding mathematician that was willing to listen to my ideas in an extremely friendly way. And at this conference in Berkeley, we immediately wrote an article together. And since then, we have developed a relationship that goes far beyond mathematics. So Michelle, as you know, I cannot be physically present there, but I would like to wish you an happy birthday and all the very best for the future. Okay, so now back to math. Okay, I would like to talk about the Grothendieck group, the Grothendieck ring of varieties. Let's start with some notation, little k for our base field. Let me write var little k. This will stand for the category of algebraic varieties. And by this, I mean reduced separated k-scheme of finite type. And let me start with the main definition of this Grothendieck ring of varieties. Which I will use the following notation, so k0 var little k. So just one comment, this was introduced in a letter from Grothendieck to Serre. A long time ago, it was in 16 of August of 1964. And this ring is pretty easy to define. So we define it in terms of generators and relations. So we'll have one generator for each isomorphism class. So with X, an algebraic variety. And we have the following relations. So we impose that the class of X is equal to the class of Z plus the class of X except Z. So in this, whenever we have a closed subscheme inside of X, so these relations are usually called the Scissor relations. So the idea is that if you have your variety X and your closed subvariety Z and your complement, well, on the Grothendieck ring of varieties, it doesn't matter how Z and its complement are glued together, it only matters the pieces. So this is the kind of information that is lost when we pass from varieties to this Grothendieck ring of varieties. And it is a ring, so far it's just a group. It is a ring, it has a multiplication, and as you expect, the multiplication is simply induced by the product of X and Y over your base field. So there are many things that one can say about this Grothendieck ring of varieties. Let me just write one sentence, that although it was defined a long time ago, this ring is still very complicated. And it's even quite mysterious. So let me put this as a slogan. And today I just would like to focus in one particular feature of this ring, which is the following. Suppose that you have two algebraic varieties that have the same class in the Grothendieck ring. Does this imply that they are actually isomorphic to each other? Well, this doesn't seem very reasonable. So we can immediately say, well, no, this is false in general. So let's see an example here. So an example where it fails. So suppose that for x, we choose the affine line. So let's choose the affine line. And for y, we choose this ordinary cusp, so spec ring with two variables, and we impose the relation that x cubed minus y squared vanished. So geometrically, we can draw it something like this. And clearly, these two algebraic varieties are not isomorphic. One is smooth, the other is not even smooth. But nevertheless, they are piecewise isomorphic in the sense that we can find these closed subschemes inside of each one of these algebraic varieties, which are in fact the same. So we have this red region and this green region. They are the same, but they are glued in a different way. So you end up with different schemes. But since we are using exactly the same pieces in the Grothendieck varieties, these two algebraic varieties have the same Grothendieck class. So they are not isomorphic, but nevertheless, they are piecewise isomorphic. So you see, there are a lot of identifications that occur in the Grothendieck ring of varieties. You cannot expect that if they have the same Grothendieck class, that they are isomorphic. And it's even the case, then if you see this, you can wonder, maybe that's the case, that if you have two algebraic varieties that have the same Grothendieck class, maybe the reason that's behind of this is that they are actually piecewise isomorphic. And that turns out not to be the case. There are examples in the literature of algebraic varieties which are not piecewise isomorphic, but nevertheless still have the same Grothendieck class. So it's difficult to control all these relations that occur. So it's really false in general. And what I would like to say is that surprisingly, it's also true in many cases. And this is what I would like to explain today. So what are those cases where we actually have this kind of isomorphism? So let me do a statement of results. So I will first talk about quadrics. So here, the base field, I will assume it to have characteristic 0. And then suppose that we have a quadratic form. So we have a quadratic form. And I'm going to assume that it's going to be finite dimensional and non-degenerate. And then there are a lot of things that we can assign to our quadratic form. So for example, we can look at its dimension. We can look at its discriminant. So this is nothing but a signed version of the determinant. So we have, so let's call it n, the dimension, minus 1 over 2, and then the determinant of q. And this is well defined if you see it in this group of square classes. And this is defined when the dimension of your quadric is even. So you can define its discriminant. It's or sometimes called the signed determinant. Another invariant is the even Clifford algebra that you can associate with your quadratic form. You can look at also to the quadric hypersurface inside of this projective space. And in the case where your base field is formally real, the case that is formally real, you also can look at the signature of your quadratic form with respect to an ordering of your base field. So P stands for an ordering of your base field K, and this will be an integer. So there are a lot of invariants that we can assign to quadratic form. And the first result, so theorem number 1, says the following. Suppose that you have two quadrics, so two quadrics that have the same Grothendieck class, then it turns out that they have the same even Clifford algebra. And in the case we are working with a formally real field, the signature of these quadratic forms is also the same. Not quite, the absolute value is the same. So you see these two invariants, this theorem is basically telling you that these two invariants are insensitive to this Scissor relation. So the even Clifford algebra and the signature. And just a remark that from the even Clifford algebra, if you know that they are isomorphic, you can also conclude that the determinant, the discriminant of these quadratic forms is actually the same. So all these invariants that I mentioned are actually well defined on the Grothendieck ring of right. And this yields immediately some applications, because in many cases these invariants actually characterize your quadratic form. So application number one is the following. So suppose that you have two quadrics that have the same Grothendieck class, then it turns out that they are actually isomorphic to each other. And this happens, for example, when you are in low dimensions, when the dimension of this quadratic form is less or equal than 4. So this, I should say, maybe I forgot, that the dimension is something well defined in the Grothendieck ring of variety. So if two algebraic varieties have the same Grothendieck class, they have the same dimension. So when I'm writing just dimension of Q to be less or equal than 4, that's equivalent to the dimension of Q prime. So that's why I don't need it to write. So in low dimensions, so in the case of curves and surfaces, you have this result. And also you have a condition on fields. So suppose that your field is such that when you look at this fundamental ideal of this Witt ring of quadratic forms, you look at the third power and you ask it to be torsion free. So it's a condition on your base field, which holds, for example, whenever is K is a local or a global field. So in this case, again, this implication holds. So the quadratic forms, if you have two quadratic forms, if you have two quadrics that are non-isomorphic, then the corresponding Grothendieck classes remain distinct. So another way to rephrase this, we can say that if you look at the quadrics, you look at the set of all quadrics, and you mod out by the relation of isomorphism, then this set actually it's inside the Grothendieck ring of varieties. There are no identifications that occur in the Grothendieck ring of varieties. So this is the solvent in terms of quadratic forms. Let's see some examples in the case of local and global fields. Let's see some examples in dimension 2 of surfaces. So for example, let's say that we are working over the reals. So if you are working over the reals, there are not so many quadric surfaces, or equivalently, there are not so many quadratic forms up to similarity. Up to similarity, there are only 3 of them. So you have this one, you have this one, and you have this one. So you have these 3 quadric surfaces that are non-isomorphic, and the Grothendieck classes remain distinct in this particular case. Of course, this is because the field is rather simple. Other examples, suppose that you are all working over the p-adix to simplify p different from 2. So if you choose a unit, so if you choose a unit with the property that such that when you take the residue class here, z mod pz, and you impose it not to be a square. So using this notation, in fact, there are 6 quadric surfaces, non-isomorphic, so you actually get distinct Grothendieck classes, and they are exactly the following ones. So you have this one, you have this one, you have this one. This one. This one. And finally, this one. So these 6 quadric surfaces, they actually, they are the only 6 quadric surfaces that exist over the p-adics, and they remain, the Grothendieck classes remain distinct. Okay, so far everything is finite. So let's see an example. So if you go to an example for the rationals, here you have infinitely many quadric surfaces. For example, we have the following family. Here we have this following family indexed on those prime numbers which are congruent to 3 mod 4. So here we have this infinite family. So I'm not saying that these are all possible quadric surfaces. They are not. In contrast with the previous 2 examples, I'm just giving you a family, an infinite family of non-isomorphic quadric surface. And note that in this family, all elements have trivial discriminant, which is p squared. It's a square. So we can also give you, for example, another family where the discriminants are all different. For example, 1, 1, 1 alpha, indexed on the square classes. So you can index them on the square classes. And this group, so again, it's an infinite family. And again, this group of square classes in the case of the rationals is quite big. So it turns out to be isomorphic. You can write it as follows: as a quotient of this group plus or minus 1 times, and then you have a bunch of copies of Z indexed on the prime numbers, and then you mod out by this subgroup where you have a bunch of copies of 2Z. So you see that this group of square classes is huge. So we have this huge infinite family. Every element has a different discriminant from the other. So we have all these different Grothendieck classes. So in these examples, in these particular examples of these fields, since they are local and global, it turns out that any 2 quadratic forms that are non-isomorphic will have a distinct Grothendieck class. Okay, so this is almost a perfect result in the world of quadrics. Everything remains distinct. And now we can try to generalize this and go one step further and go to a generalization of quadrics, which is called involution varieties. So what can we say about here? So again, finding characteristic 0. And now instead of starting with a quadratic form, I start with a pair. So I have a central simple K algebra. And I have equipped with an involution of orthogonal type. And then there are a lot of things that we can assign to this vector. For example, the degree. So this is by definition the square root of the dimension of A. Again, we can define a discriminant. This is a well-defined element in this group of square classes. And this is well-defined when the degree is even. Also, we can define the even Clifford algebra. We can also define the analog of our quadric would be something called an involution variety that I will explain. And also we can talk about signature with respect to ordering. And in this case will be a natural number. And this when K is formally real. So maybe here, let me say some words about the involution varieties. Let me define it in a very precise way and then in a conceptual way. So in a very precise way, we can say the following. So would be some kind of the analog of the Severi-Brouwer varieties. We can look at the right ideals. So the right ideals are I inside of A of dimension degree of A. And now if I stop there, I just get the Severi-Brouwer variety, but I impose a condition, which is this condition that I star I be at 0. And you can see this as a closed subvariety inside of the Grassmannian of A, consider it as a vector space, and then subspaces of dimension a degree of A. So you can see it in this, you can define it in this very explicit way, but conceptually, what are they? So they are exactly the twists of the quadratic forms. So there is this bijection between central simple K algebras with evolutions of orthogonal type. So let's fix the dimension, in this case the degree. Let's say that the degree of A is D. So you can look at the set, and then you can mod out by the isomorphism, so up to isomorphism. So there is a one-to-one correspondence with, on the other side, you have the smooth projective K varieties, X of dimension D minus 2, so and such that where they have the following property that when you base change to the algebraic closure of K, what you get is the unique quadratic form that exists over there. So you get x squared plus etc. X squared d minus 1. You get this equals 0 inside of this projective space d minus 1 over the K bar. And you consider them up to isomorphism. And the bijection is given by we assign to this central simple algebra with involution, the involution variety. So this tells you conceptually what they are. They are precisely the twisted forms of the quadrics. So let's see some examples. And of course, the first example are the quadrics themselves. So if A is split, then this implies that the evolution is necessarily of the following form, is necessarily the adjoint evolution of a quadratic form, which is well defined up to similarity. So this is going to imply that in fact the involution variety reduces to the quadratic form. Sorry, to the quadric hypersurface. And an important remark is that if suppose that we are in such a situation with the degree of A to be odd, then in this case, it's because A is split. So there are no interesting evolutions of orthogonal type in central simple algebras of odd degree. They all come from quadrics. So this evolution varieties only exist somehow in even dimensions. So let me give an example of a true evolution variety. For example, products of two conics. So let me remind you, so when you have a quaternion algebra, you can assign to it the corresponding conic, which is defined as follows. So you take minus a square minus y square, and then here plus ab z square equals 0. So we have this conic inside of P2. And it turns out that if the degree of A is 4, and the discriminant is trivial, in other words, it is a square, then this implies that your central simple algebra equipped with involution, it's actually isomorphic to a quaternion algebra equipped with this canonical involution tensor, another quaternion algebra equipped with this involution. And then it turns out that this implies that the corresponding involution variety is actually isomorphic to the conic of this quaternion algebra times the conic of this quaternion algebra. So if the central simple algebra is degree 4 and trivial discriminant, then what we are talking about is products of two conics. That's what it is, these involution varieties. They become, they reduce to products of two conics. So maybe let's go one step back and let's come back to our previous examples. And so here we are in the case of degree 4. And so we need to understand where we have a trivial discriminant. Clearly, the first two, we are in a situation of trivial discriminant. So these are the two cases. And it turns out that in this case, well, what's happening is that we have a product of these two conics, which turns out to be just a product of two copies of P1. And in the second case, we actually have a product of two conics. So you look at the Hamilton's quaternions, look the conic associated with, and you have a product like this. But as you know, over the reals, there are only two quaternion algebras up to isomorphism, the Hamilton's quaternions and the split one. So in fact, it turns out that one involution variety here is missing. So you still have this product of two conics that is still missing here. In this example, so if we search for the cases where we have trivial discriminants, well, they are precisely the first two. So in these cases, we have trivial discriminant. So in the first case, again, we have two copies of P1. And in the second case, we have a copy. Here we have epsilon P, it's quaternion algebra cross epsilon P. But so again, in this local field, there are only two quaternion algebras up to isomorphism. And so there is still one involution variety that is missing here. And as in the previous case is exactly this one. So this involution variety is there and it's not applied. And if you go to the reals, well, to the rational numbers here, well, things are huge. The example becomes much more complicated. You can have any kind of, so in the first case, they are trivial discriminant, but so you have products of all these possibilities for any two possible quaternion algebras. And in the case of the rationals, the quaternion algebras turns out to be parameterized by those square-free positive integers, in fact. So you see that it's really huge, this family of products of two conics. Okay, so now with these notations, so what can we say? We can say the following. It turns out that theorem 1 and application 1 admit a generalization. We have the following theorem 2, which is as follows. It says that if two involution varieties have the same Grothendieck class, then it turns out that both the even Clifford algebra is the same, as well as the signature for any ordering of our base field, it's actually the same. And once again, from the even Clifford algebra, we can conclude that the discriminants are also the same. And here, there's no need to use the absolute value of the signature, because in this case, the signature will be a natural number. Okay, and Similarly, these invariants carry a lot of information about involution varieties. So we also have the following application number 2, which is as follows. So it says, as you expect, that if two involution varieties have the same Grothendieck class, then it's because they are actually isomorphic to each other. And again, once again, in the following cases, when you are in low dimensions, or when the base field satisfies this condition, that the third power of the fundamental ideal is actually torsion-free. And this is the case, for example, for local and global fields. So this theorem 2 and application 2 are far-reaching generalizations of theorem 1 and application 1, but the way I state them, they are actually false. So we need to pay attention to the following assumption. So there is an assumption that I need to specify. So what is it? So the assumption is as follows, is we need to assume, so the assumption for both the application and both the theorem is that we need to assume that A and A prime, they are actually split when the following holds, when we have the degree of 8 equals 4 and the discriminant would be trivial. So this condition here, as I mentioned, I'm only writing it for A because in fact, if two involution varieties have the same Grothendieck class, this condition runs for one of them if and only it holds for the other one. So I'm only writing it for A. And what I'm asking here in this assumption is basically that when I'm inside the square, I'm just saying that we are in the case of products of two conics. I'm just saying that A and A prime are split. So geometrically, what am I saying here in this assumption is that my involution variety, which I know that it's a product of two conics, it's actually a product of just a conic with itself, and same story for the other involution variety. So these assumptions might seem a little bit strange, and we may wonder if the theorems and the application still hold without this assumption. So let me just mention that even with the assumption, theorem 2 and theorem 1 are far-reaching generalizations of theorem 1 and application 1. So why one may wonder if the theorem still holds without this assumption, and it turns out that that is not the case. The theorem is false, and this is what was previously explained by a theorem of Collar that says the following. Suppose that you have 4 quaternion algebras. So they are quaternion algebras. And the following are equivalent. So first of all, this product of these two conics, so they have the same Grothendieck class. So they have the same Grothendieck class if and only if these two products are actually birational to each other. So if this is birational to this product, and also that's equivalent to say that when you look at the Brouwer group, you look at these Brouwer classes and look at the smallest subgroup of the Brouwer group generated by them, well, they both generate the same subgroup. So this is happening in the Brouwer group. So from this theorem of Collar, we immediately see that the theorem 1, 2, and application 2 cannot be true without this assumption. And let me give you an explicit example where the theorems fail. So this example again, let's say that we are working over the reals. So in this case, suppose that you choose, for the first one, you choose the Hamilton's quaternions. For this one, you just choose the split one. And for the other two, you choose the Hamilton's quaternions. Then you can define, so let's consider this one as the tensor product of this one with this canonical involution, tensor product this one with this canonical involution, and same story with the prime. So what can we say here? First of all, look at the subgroup generated by the Hamilton's quaternions and the split one that actually generates the same subgroup in the Brauer group as this one. So this, thanks to Collard's result, this implies that in fact the Grothendieck class of this product of two conics, it's the same as this product of two conics. But another way to say this is say that the Grothendieck class of the involution variety of A is the Grothendieck class of the involution variety of A prime. So here we have two central simple algebras with the involutions of orthogonal type, such that the involution varieties have the same Grothendieck class, but now we'll see that they have all different invariants. So first of all, when you look at the even Clifford algebra of this one, well, that turns out to be the quaternions times the split one. Sorry, this is not the minus. In contrast, the even Clifford, and so this is not isomorphic to the quaternions times themselves, which is the even Clifford algebra of this one. So the even Clifford algebra is not an invariant. If you look at the signature, so we are over the reals, so there's only one possible ordering. The signature of this one turns out to be 0, and 0 is different from 4, because 4 is actually the absolute value of the signature of this quadratic form, and this is the signature of this one, of A prime, A prime. So you see that A prime, it's a tensor of K1 prime and Q2 prime. So you see that it's split. So you are working with the quadric. The quadric is precisely this one, which has signature 4. So again, the signatures fail. They are not the same. And also, of course, the invariant involution varieties, that they are not isomorphic. This one is this conic times P1, which is not isomorphic with this product of these conics, which is the involution variety of prime. So this tells you that, in fact, this condition, this assumption is needed for both application 2 and theorem 2. And if you plug it to application 2, if you combine application 2 with Collard's theorem, we actually have a complete understanding of all the Grothendieck classes. So let me come back to our previous examples here and be more precise. So if we are over the reals, so over the reals, there are no other involution varieties. So we have three quadrics and 4 involution varieties. And in this world of products of two conics, we have 3 products of two conics, but has Collard showed. So in fact, these two have the same Grothendieck class. So although we have 4 involution varieties up to isomorphism, we only have 3 Grothendieck classes. This is the only identification that occurs. Again, so here, if we are in the world of the periodics, we have these 6 quadrics, but it turns out that there are other involution varieties that are not quadrics. Let me just write them. So they are, let me put it on the right-hand side. they are involution varieties coming from something called a norm construction. So in the periodics, you can join the square root of epsilon, and we consider this extension. And here, so in this local field, there is a unique non-split quaternion algebra. Let me call it P. It's a unique division algebra. And then you can do something called the norm construction that will give you a central symbol algebra equipped with an involution, and you get a different involution variety, which is not a conic, which is not a quadric. And again, there's another one coming from the norm construction associated when you add the square root of P. And there's a unique division algebra over there, and you do the construction. So in fact, it turns out that we have 6 quadrics, so 6 quadric surfaces and 9 involution varieties. And then if we restrict ourselves to these cases of products of 2 conics, we have 3 of them. And again, we have this, thanks to the result of Collar, we have this identification. So once again, although we have 9 involution varieties, we only have 8 Grothendieck classes. So this is the kind of phenomenon that is occurring. And in the case of the rational numbers, okay, everything becomes much more complicated. Then I just mentioned that the involution varieties that can be of dimension 2, they can be parameterized, in fact, by the quaternion algebras, which leave over some étale quadratic extension of the rational numbers. So here you have infinitely many examples, and it becomes infinitely much more complicated. Yeah, I still have some time, so maybe let me make a picture just to give a feeling. If we put both theorems together, one way to think about this is to say the following. So here we have the quadrics. So we have the quadrics, and also a generalization would be the involution varieties that are here. And then we have something here, which are the products of 2 conics. And they all live inside, so they all live inside the Grothendieck ring of varieties. And the point is that if you are in the green region, you just need to think about them up to isomorphism. So up to isomorphism, you can embed the quadrics inside the Grothendieck ring of varieties and in the involution varieties. And if you are in this small piece of the product of 2 conics, here you need to think about them not up to isomorphism, but up to birationality. If you do this, then we actually have an embedding inside of the Grothendieck ring of varieties. Okay, so I think now would be a good idea to finish by giving a sketch of the proof, a very, very brief sketch of the proof. And let me just do this sketch. So it would be a sketch of half, in fact, of half proof, let's say of theorem 1 to simplify the case of quadrics. So there are 2 main ingredients. One ingredient is that there is a well-defined motivic measure with values in something called, we can do the following. So in the same way that we can define a category of Chow motives, this was originally done by Grothendieck, there is a non-commutative analog. So this is why I wrote this N here. And it's a category, a symmetric one-arrow category. So you can take its Grothendieck ring, and there is a motivic measure that assigns a smooth projective variety. You can do the following. You can look at its perfect complexes, well equipped with some DG enhancement, And then you can see this BG category inside this category of motive. So we have some kind of invariant, universal invariant, and they then take its Grothendieck class. So you have this motivic measure. And now you just need to use it. So if suppose that you have two quadrics that have the same Grothendieck class, then they necessarily would have the same motivic measure. So in other words, this is saying that the Grothendieck class of this non-commutative Chow motive is the same as the Grothendieck class of this non-commutative Chow motive. Sorry, this X, of course, it's not an X, it's a quadric. Too fast. So here it's the quadric, and here it's the other quadric. But then concretely, what does it mean to have the same Grothendieck class? That means that you have an object there as non-commutative Chow motive, such that when you add up with this one, you get an isomorphism. You get an isomorphism, and now we can use the following. So the category of perfect complexes on a quadric, it was described by Kaplanov. So this, in fact, turns out to be equivalent. So here you have M, and then we have a bunch of copies of our base field, as many as the dimension of my quadric. And then one thing is missing is the even Clifford algebra. So this was established by Kaplanov. So we have an isomorphism of this form. Here it's the dimension of Q prime, and then we have the even Clifford algebra of Q prime. And then, so you see that you have the same, since they have the same Grothendieck class, the dimensions are the same. So these both dimensions are the same. So you see that you have the same thing on the both sides. So you would like to cancel it. And it turns out that in a previous article with Michel, we described this subcategory inside of the non-commutative Chow motives consisting of the separable algebras, and the even Clifford algebra is actually a separable algebra. So by pushing forward this kind of description, it turns out that one can prove a cancellation result. So using this result with Michel, which plays really a key role here, we can actually cancel this and conclude that actually these non-commutative motives are isomorphic. And from here, we can conclude that actually the simple algebras, that the even Clifford algebras are isomorphic to each other. So this is what happens for this invariant. And in the case of the signatures, what's happening is that we need to use not the non-commutative Chow motives, but actually the classical Chow motives, and using them and some kind of an analog motivic measure, we can actually prove that the signatures do not change again. Okay, I think my time is up. I think this already gives you an idea of what's happening, at least with this class of varieties inside of the Grothendieck ring of varieties. And so to finish, let me just maybe display the last blackboard that I wrote with Michel. It was at EHOS, so just it stays there. Thank you, Michel. Thank you for listening.
Thank you.